it's just a projector screen. And like last week, I go and I ask for the screen to come down, and it like hits this point, and it just keeps going, and it just keeps going. It hits the floor, and then it like piles up into this like friggin' thing on the floor. So I'm like teaching my lesson on Java, and we're going to take a brief interlude to talk about friendship and how friendship is magic. So, yes. So let's recall our example from the previous topic. That number is incorrect. Wait, no, it isn't. Okay. In geometry, certain types of figures may be defined by a collection of points. In the following example, we will define a triangle class using class composition. When classes use objects of other classes as member data, this is called composition. A triangle has 3 points, so our triangle class will also contain 3-point objects. For this example, we won't make too big a deal out of public versus private variables. We've kind of established that stuff, so we'll just, keep going. We're primarily interested in things being containers for data at this point. So, composition of classes. We have our class point. Has 3 doubles, x, y, and z. We have a constructor. The constructor is doing nothing except assigning the 3 input parameters to the constructor to their respective data elements. We have a distance to method, which allows, we covered this last time. This is the same point class that we dealt with last time. Now we have class triangle. We have 3 public points, A, B, and C. A triangle takes as arguments to its constructor 3 objects of the point class. So in this particular instance, we need these point objects to be created prior to the triangle being created. Now this is one particular approach, You might do another approach where these points are created, these point objects are instantiated inside the constructor. You can do it that way too. It's kind of 6 to 1, half a dozen to the other. So we have a method to calculate the area of this triangle using Heron's formula. So we have a semi-perimeter, S. We have the length of AB, BC, and CA, each using A dot distance to B, B dot distance to C, C dot distance to A. There we go. Semi-perimeter is it's a private method that's included in the triangle class, if you were wondering where that came from. S is S times S minus AB times S minus BC times S minus CA, and then we return the square root of that. This is a fancy, complicated means of calculating the area of a triangle using the side lengths and the semi-perimeter. Semi-perimeter, of course, A distance to B, B distance to C, C distance to A, all summed, so that is the perimeter divided by 2. So the semi-perimeter is just the perimeter in half. So it's the, it's the distance around half the figure. In main, we have our triangle T. This is a class. This is an object instantiation. So triangle T is a triangle receiving points 0, 0, 0, 0, 4, 0, and 3, 4, 0, respectively. Notice that these, we're including the constructors for these point objects inside of the call to the point, to the constructor for the triangle object, right? So we're sort of nesting these constructors in themselves in order to, save having to declare intermediate variables. Because there'd really be no point in declaring a variable in main for each of these points, right? Anyway, so see out the area of the triangle is T dot area. There we go. Graphing said triangle, we come up with the following. We have from 0, 0, 0 to 0, 4, 0, or 0, 0, 4, you know, those are the coordinates, right? Make sense? Good. So, the area of the triangle is 6, and I'm sure if we, you know, if you did it out, this is a right angle triangle, very easy to calculate the area of. As we can see, using an object within a class is the same as using it anywhere else. Composition produces a hierarchy of objects, and it introduces the idea of parent and child classes. So the parent is the class that has the subclasses, which are the children, right? A child object must be initialized via the initialization list. See topic 10, slide 34. So when you're initializing sub-objects or child objects, you have to do it this way in C++. Most of the time, when you are working with object hierarchies in computer programs, you are working with a compositional hierarchy. Most object hierarchies are compositional. Let's expand this idea to tetrahedrons. Ooh. So, a tetrahedron, what's a tetrahedron? Yes? It is. It's a three-sided pyramid. In Dungeons and Dragons terms, it's a D4, right? Tetrahedron. So, of course, this would be an irregular tetrahedron because the points can be, like, warped around, right? So, this is kind of a slightly interesting definition. So we have triangles A, B, C, and D defined inside of our tetrahedron class, but you can see we're initializing a tetrahedron by the locations of their, the location of the four corners in space. So we are taking these points and constructing the triangles from these points, which are defining the corners of the tetrahedron, so that we can store it as a triangle, right? In theory, we could also define a tetrahedron using 4 points instead of 4 triangles, but then we wouldn't be able to do interesting things like calculate the surface area of the tetrahedron, right? Or at least we would need to re-implement stuff that we'd already put in the triangle class in order to be able to do that, right? Code reuse. Code reuse is the name of the game. So surface area is, of course, just the sum of all of the areas of all of the triangles composing the tetrahedron. Make sense? Good. So, in terms of our, so this is, do we have the name now? Okay. So this is the tetrahedron that we might define using these points in space. We have the following class hierarchy diagram, right? So we've got one tetrahedron requires 4 triangles. Each of these 4 triangles requires 1 point, or 3 points, pardon me. So the 4 triangles that compose a tetrahedron require some constraints in order that they might actually form a tetrahedron. A tetrahedron has only 4 points shared among 4 triangles. Our class encoding allows a tetrahedron to be constructed only from its vertexes via construction of a data policy. So the constructor enforces a data policy whereby each of the triangles composing the tetrahedron must be one of 4 points given to the constructor that define the corners, right? This is not to say that after the fact, some person or method might come in and like yank one of the corners of one of the triangles and like, you know, open the tetrahedron down like it's, you know, like it's a spaceship pulling its landing, you know, runway down. You know what I'm talking about. War of, like, what is it called? The Day the Earth Stood Still with the thing that comes out. Anyway, So just because this constructor enforces a data policy doesn't mean that other things couldn't violate it, especially because we've made the triangles themselves public. But if we put the triangles behind a privacy barrier, if we made them private, then, and if every method, like if no method allowed a point of one triangle to remove itself from the points of the two other triangles that it forms a point with, then the tetrahedron would never not be a regular, or it would never not be a tetrahedron. Make sense? Okay. Any questions? Yes?
What would happen if, like, I don't know, you put all those points in, like, a line or something?
It's still a tetrahedron. I mean, here's, I think that you might be placing an implicit condition on triangles there. You might be placing the implicit condition that a triangle must have a non-zero area to be a triangle.
Yeah.
Right? But, you know, is that actually a condition of triangles? You know? Is that not a triangle?
I would say no.
I mean, sure, but what's the definition of a triangle?
3 sides.
3 sides and three corners, 3 sides, right?
Yeah.
Distinct,
Distinct?
but they can't be the same.
I mean, if you have, so AB is distinct, BC is distinct, CA also distinct, I would argue. It's not the same as AB or BC. It's the sum of the two, right? Yeah?
Wikipedia says that in Euclidean geometry, any 3 points when non-collinear determine the triangle.
Ah, okay. All right. So they have to be non-collinear. Okay. So that's not a triangle then.
But only in Euclidean geometry.
Right. Exactly.
What other kinds of geometry are there?
Oh, spherical geometry is a non-Euclidean geometry. Like geometry on the surface of a sphere. Yeah. Which it turns out to be, it turns out that that's actually kind of useful when you live on a planet. Right? So, because on the surface of a sphere, the shortest distance between 2 points is not necessarily a single straight line, right?
It's a one line.
That's why, you know,
It's great.
if you have the planet and you're trying to fly from here to there are like a number of different paths you can take, which are, you know, of roughly, like, you can take 2 paths that are both of equivalent distance, right? So, whereas in Euclidean geometry, there would only be one path between 2 points that is the shortest, right? So, yeah. Okay. So how would we fix that then? How would we fix this definition so that we couldn't just like specify 4 points that were all the same point and call a point a tetrahedron because there's 4 of them in one location?
Can you have like an if statement in your constructor?
Mm-hmm. Yeah. So what you could do is you could take your triangle class, right? In the constructor, you could raise an exception or throw an exception if these points are collinear. But then you would need to be able, like, you would have to write something to calculate if points were collinear. Where would we put a method to tell if points are collinear? Would we put that in the triangle class?
In the point class?
We would put it in the point class. So if we add a test to see if 3 points are collinear in the point class, we can use that method to gate whether or not a triangle is a triangle in Euclidean geometry. And And then, so long as these 3 points weren't collinear, and so long as these, it might be a very irregular tetrahedron, right? Because a point does not have to be far off to not be collinear, right? Like, if I could draw more accurately, that's a triangle. Technically, though, you could take a bunch of these and make a tetrahedron, right? Yes?
Would it make sense to make the collinear method part of the point class if it would require multiple points to like determine?
How would you figure it out?
Well, we're already using the distance too, it takes another point, right? So if where is our point? Is this the point? Yeah. So the way I would do it, I would just write is collinear, takes 2 points, and then just returns a Boolean true false if they're collinear or not, right? So yeah, it's like you check to see if point A is collinear with respect to 2 other input points, B and C, I would say. Yes.
You not just check if the area is 0 instead of resolve.
Yeah, you can do it that way too. In theory, yeah. Although I don't know if Huron's formula is applicable if the triangle isn't a triangle as defined by Euclid, right? I don't know if like that breaks this, maybe it does, maybe it doesn't. But yeah. Okay, enough about geometry. So, so let's talk about friendship. Lessons about friendship. Here we go. In C++, there is a somewhat odd concept of friendship among classes. Friends get certain privileges, specifically access to a class's private members. Boy, the class usually just breaks into fits of hysterical giggling at that point. Okay. A class may designate both functions and classes as friends. This is a controversial, people are starting to get it, there we go. This is a controversial feature because it violates the principle of encapsulation. It is up to a class to determine who its friends are. You can't force a class or a function to be friends with another class.
I missed it.
Thank you, there we go.
I missed the private members part. That's
So-
what I just said.
There we go. So you make a function, you make something a friend by providing a function prototype or class declaration with the friend tag in the class that you wish to give it access to. So just like in real life, you can't force someone to be your friend. They have to decide to be your friend, right? Life lessons. So here we go. Let's imagine we have classes A and B. Class A has a private Q, class B has a private B. A has Q is equal to 0 and makes B a friend. Therefore, B has access to show A. Well, it defines its own method, show A, which takes some A and produces, it basically just prints its private member out. Make sense? Sort of? Yes?
What's with the A ampersand?
Is that on the next slide? It's passing by reference. So, so this is passing by reference in C, which hopefully everybody remembers. You can still do this in C++, but now we have an alternative that doesn't require pointers pass by reference. So this is pass by reference. It's slightly different from address of and then passing the address in because if you if you take a look here, we're just using x.q. We're not dereferencing x. So it's like, and this is like another one of those funny little C++ things. If you put the ampersand on this side, it means it's a pointer, and then you have to dereference it over here. But if you put the ampersand on the other side, it's not a pointer, it's a reference to the object. And then you can just use dot syntax to access the members. So both are equivalent. This one requires less pointer fiddling, which is probably preferable because pointers are hard. Questions?
Like a question. The pointer, like using C++, it's not the same as C, right?
No, it is.
It is?
Yeah.
So yes.
Yes, so all C is in C++ somewhere, right? You can use everything that you learned in C in C++. The thing is that C++ understands the problems in C, and it's trying to provide you some alternatives that don't require explicit pointer manipulation, right? That's what it's trying to do here. It's trying to give you a way of, like, you know, like the difference would be that if this wasn't a reference to some A, then it would create a new instance of it, right? Because it's passed by value, and that includes classes. Make sense? Okay, cool. Any other questions? So then in main, if we declare A and B and we show A dot A, or we B dot show A, that's not normally possible because Q is private, right? So, wait, did I do a typo? No, I didn't. Okay. Should say show Q here, but anyway. So yeah, it prints out its private member because it's friends. That B is A's friend. But interestingly enough, A has made B A's friend, but B the relationship is not reciprocal. B would have to also explicitly make A its friend in order for that to be a bidirectional relationship. So, the natural state of friendship in C++ is unrequited. So, there we go. Can you tell I had fun with these slides? So how is this different from pointers? Pointers can be reassigned or assigned null. References cannot. Pointer arithmetic does not work on references. References don't need to be dereferenced, ironically enough. References can never be uninitialized or point to something that isn't a valid memory sector. That's very interesting and important. So there's no possibility of a segfault with it. References lack the flexibility of pointers, including dynamic allocation. So you can't dynamically allocate to a reference. So there still is a purpose in C++ for using pointers because you can use dynamic allocation on them. Whereas C++ sort of prefers you don't worry about that kind of low-level stuff. Using references allows the benefits of in-place memory operations without the muss and fuss of perpetual pointer problematization. Questions? Cool. So, so let's talk about inheritance and how none of us are going to get any. Because nursing homes are so expensive. So, in object-oriented programming, we extend a class using inheritance. This is a very, very different concept from composition. People will very often confuse inheritance and composition, mostly, I think, because when discussions like this of object-oriented programming come about, composition isn't even talked about sometimes, and they just talk about inheritance because, like, when you read the course outline, it's like, you will talk about inheritance, and it's like, okay, sure, but in order to understand the difference between inheritance and composition, you have to know what both mean, right? But anyway, so in general, inheritance is a poorly understood concept and is often confused with composition. If one class uses or is built from other classes, you want composition. See our tetrahedron example. If one class is a variation on another, with additional members or some members redefined, that's a situation where you want inheritance. Did they talk about inheritance with you guys in Eng 1? Not even a little bit? You did classes, but they didn't even mention the concept of inheritance?
Nope.
Okay, all right. So it goes. So, when one class inherits another, that class gains all of the members of the class it inherits from, without needing to redefine them. So, we'll get to examples. Remember, a good engineer always uses the right tool for the job, and that means knowing when to use inheritance versus composition. So, the class which does the inheriting is known as the derived class. The class from which the derived class inherits is known as the base class. So, derived classes are built from base classes. The derived class has a more specialized or specific behavior, whereas the base class is more general. So, for example, and this is like when you're talking about inheritance, like the animal kingdom is a very common example. That's kind of like, if you think of a spider, right, it is several things at once. It is in the kingdom Animalia, it is in the phylum Arthropoda, it is in the, I don't know what the names are after this point. Does anybody know what comes after phylum?
Class,
Class?
order.
Ah,
family,
class,
genus,
order?
species.
Oh, classes, right? So, class Chelicerata and order Arachnida. And this is how you define a spider, right? So the idea is, all arthropods are animals, not all animals are arthropods, right? So, in order for the idea of an animal to mean anything, it must be general enough to define everything that could be an animal, right? And since there are an awful lot of different types of animals, it must be a very general thing indeed, right? So, you know, getting back into high school definitions of things, what defines an animal? It's like, I seem to recall it's something like homeostasis, right? It has to like seek the conditions for its own perpetuation, and reproduction has to be able to reproduce. But it doesn't necessarily have to move, because sponges are also animals, but they don't move. So that's all the, like, if animals were a class in C++, those are the two methods. Reproduce and, like, eat, you know? As you get down the hierarchy of living things, you get more and more specific characteristics. All arthropods share certain basic body plan characteristics. You know, all chelicerates share some particular mutation, like formation of those characteristics, and arachnids have a further, more specific sharing of those traits. We may modify the permission levels of all members of the base class by specifying either public, protected, or private inheritance. Each of the above will strengthen the protection level of members with a lower protection level than the one specified. Public inheritance is most common. So, if we have, if we are inheriting publicly, basically everything that's public, protected, or private is not modified. If we protect the inheritance, then public becomes protected, but nothing else changes. And private inheritance forces everything to become private. Let's consider an inheritance hierarchy of people in a university. The most general type of person in the university is a community member. This can be roughly categorized into employees, students, and alumni. So the base class is community member. We are all like physically existing people, so we all have positions in space and momentum and other characteristics that are common to all human beings. But the class for employees, students, and alumni are each a separate class that will inherit from the community member class. So these are all derived classes. This is the base class. Since there are no people who are community members without being one of the three above subdivisions in this example, we call the community member an abstract class. So abstract classes are only used for the purposes of inheritance. The idea is that you would never actually initialize one, right? It's just a container for data that gets inherited by other classes, which are themselves, instantiated. Going back to our arachnids example, if you had like a life simulation and you wanted to instantiate an animal, right? You would not instantiate it at the level of class animal, right? Basically, for animal species, every layer of that hierarchy down to, every layer of the hierarchy above species is an abstract class, because you would never instantiate an arthropod in the absence of more specific features, right? Although, in theory, a few of those were instantiated during the Cambrian explosion, but yeah. So, students and alumni require no further categorization, but employees can either be faculty or staff. Faculty can be administrators or teachers. It is possible, well, in this example anyway, it is possible for someone to be both an administrator and a teacher, so we can create a class accordingly. Inheritance can inherit from more than one base class via multiple inheritance. So, this is where the animal kingdom example breaks down somewhat, but we have community members. These inherit, so employee inherits from community member, faculty inherits from employee, administrator and teacher inherit from faculty, and administrator-teacher inherits from both administrator and teacher. So it picks up all of the characteristics of both administrators and teachers and everything else on its way up the hierarchy. So this is important because it's not like teacher just inherits faculty. It has the characteristics of faculty, employee, and community member. Question?
With administrator teacher, do you end up with duplicate members because teacher and administrator would have many of the same members?
Any members which are common to administrator and teacher should be stored in faculty, right? So while administrator teacher is inheriting these two classes explicitly, both these classes are inheriting this one implicitly, and that's just one of those. So it's not like it'll split the hierarchy, right? It'll recombine. You'll only have one set of faculty characteristics, because anything else would just be a namespace nightmare, right? Yes?
From the viewpoint of faculty, is employee a base class, or is it still a derived class because it's under community member?
From the perspective of faculty, employee is a base class. From the perspective of employee, it's a derived class of community member. So whether something is called a base class or a derived class is dependent on the position, sort of your frame of reference. Yes?
So it's also possible to inherit administrator teacher from a student class, right?
Say again, sorry?
It's possible too that administrator teacher inherits from a student.
For administrator teacher to also inherit student, you say? Yes, yeah.
It doesn't matter which layer it is, which happens.
Yeah, absolutely. You can, like, you could inherit from, like, for example, you know, perhaps your administrator teacher is also an alumni, right? Which, you know, is plausible. So they would also have, you know, former, you know, whatever characteristics a former student would have. You can also pack that into, like, you would probably make another class down here to separate that out, you know, administrator, teachers, alumnus, whatever, you know. Been here too long, the class.
Sorry, it's not but it's not possible to just return all the values from administrator back to the community member. You can't like just quickly back to the base.
Well, there's no reason to, right? Administrator teacher already picks up everything in community member through the inheritance hierarchy, so there's no reason for administrator teacher or any of these guys past this layer to explicitly reference back to the community member. They already have all that stuff. Make sense? Cool. Thank you very much, folks. See you.